So if you were to perform this multiplication, 8 times 9 equals 72. Okay, so how would you do that if you would be doing it on paper? So on paper, you know that you will write the number and you multiply the multiplicand. If you were to do this in a binary multiplication, so you would first write their binary values, and the multiplicand is 8. The second thing is the multiplier, which is 9 in this case, and then we have a final product pass through the different intermediate products. Okay, so this is a simple paper method. So what is the main observation that you have? The first observation is the size of product is almost double the size of both of the operands, multiplicand and multiplier. So if I say that the multiplicand is represented in m bits and multiplier is represented in n bits, then the product size would be m plus n. Okay, and how do you multiply in this paper-based method? We pick multiplier bit, okay, reading from right to left, and multiply it with the multiplicand, and keeps on generating the intermediate products, and in each iteration we keep on shifting it left. Okay, so in order to represent or keep the sizes of the intermediate products or the final product same, we can fill the empty blank spaces with all zeros. Okay, so what we are actually doing, if you observe it here, what we are doing is we are putting the multiplicand as the intermediate product. Okay, and depending on the multiplier bit, if it is 1 or 0, we add the entire multiplicand as it is, but in every iteration we keep shifting left. Okay, we keep shifting the multiplicand left, which is the intermediate product also. In the end, you add all of them together and generate the final results. So if you were to do it on a computer, so how computer calculates is follow the same procedure. Okay, it performs shifting on the multiplicand, shifting left, and it performs shifting right on the multiplier. Why shifting right? So in every iteration we pick this bit. Okay, so when we shift, for example, if you are doing it on paper, you will first multiply multiplicand with this first bit, and in the second iteration you will multiply it with the second bit, and then third, and so on, right? So what we can do is we can rather pick only the LSB, the least significant bit of multiplier. We keep shifting it right. So every time we shift it right, we will be picking up the next higher bit in the multiplier field. Okay, so this is the basic diagram for performing the multiplication. This is how the computer performs the multiplication. So as we discussed, if we take the example of 4-bit operands, the product would be 8 bits. Okay, in RISC-V we have register size of 32 bits, so the product would be 64 bits. Okay, so what we do here is we keep the multiplicand size 64 bits, because when we keep shifting it left, in order to preserve all the 32 bits data, we need to have a 64 bits storage or a 64-bit register. Okay, so we store multiplicand in a 64-bit register. Then we have a 64-bit ALU, because it takes the multiplicand, 64-bit multiplicand, and the 64-bit product. It keeps on adding and storing in the same product register. Okay, maybe this this diagram may be hard to understand right now, but when you will see in the next slide its flow chart, how the flow is executed, it will make more sense. But there is a control unit. What control unit does is it first after every iteration it shifts the multiplicand towards left, as it happens here. Okay, so multiplicand is shifted towards left, and it also checks if the multiplier bit was 1. If it was 1, then it will be added to the product, okay, to the product register. So we will first initialize product register with all zeros. Similarly, the multiplicand, the actual multiplicand operand, the 32 bits will be initialized in the right 32 bits, and the remaining 32 bits will be all be initialized with zeros. Okay, so depending on if the multiplier bit is 1, the addition is performed and the results are stored, and then it will also shift the multiplier right. So this is the multiplier. If we keep on shifting right, so we will only be checking the LSB. Okay, so let's look at the flow chart, how the algorithm executes this multiplication operation. So what we need to do first is test multiplier 0. So multiplier 0 means we are testing the multiplier bit number 0. Look at here, the multiplier bit number 0. I will explain with the example also. If it is 1, then what we need to do is add multiplicand to product and place the results in the product register. Okay, if it is not 1, if it is 0, then we need to simply shift the multiplicand towards left, shift the multiplier register bit by 1 bit towards right, and check if it was a 30-second repetition. Why we are checking for 30-second repetition here? Why not any other value? 32 is a lucky number in RISC-V. We have been repeatedly discussing 32 bits wide. The operand is 32 bits wide. So in order to multiply a 32-bit number with another 32-bit number, we have to check all the 32 bits are multiplied. So that is why we are checking if this process is repeated 32 times. Okay, if it is repeated 32 times, it means that the multiplication is performed and we can just finish the algorithm.